We live in the wrong kind of world to be described by string theory. No physicist has ever won a big prize for string theory. I can tell you with absolute certainty that it is not the real world that we live in. So we need to start over.
In a groundbreaking revelation, Leonard Susskind, one of the founding fathers of string theory and professor of theoretical physics at Stanford University, makes a stunning admission. String theory has failed, and many physicists don't know what to do.
They're scared. They might not get a job.
The theory that once promised to unify physics has instead generated 10 to the 500 different possible solutions, or vacuum states. Some theorists maintain that each mathematical solution corresponds to a physical reality, a legion of multiverses. However, the extensive efforts to tame this so-called landscape through, for instance, KKLT vacuous stabilization mechanisms suggest an implicit acknowledgement that the multitude of universes is senseless. I'm Curt Jaimungal, and on this channel, I explore unification in physics and philosophy using my background in mathematical physics from the University of Toronto. Today, it's a special treat since we have the legendary Leonard Susskind in rare, candid form, revealing his unconfined thoughts for the first time.
We should certainly be on the lookout for ideas which are not the consensus. We should be watching for them and not immediately dismiss them.
We also talk about what it means that the universe is a hologram, why quantum entanglement is equivalent to wormholes, why supersymmetry is absent in our universe, why we lack a quantum description of de Sitter space, and why young physicists are afraid, even discouraged, to tackle these fundamental problems. Professor Leonard Susskind, welcome to the Theories of Everything podcast. It's been years since I've wanted to speak with you, and I'm glad to be able to get this opportunity.
Glad to be here.
What are you most excited about in physics today?
That's a very hard question. I'm excited about a different thing almost every day. Ask me an easier question.
Okay, how about today in particular? You said that you have some deadlines, so why don't you talk about what you're working on?
Well, I've been working on for some period of time, trying to understand the quantum mechanics of cosmological descriptions of the universe. Technically, it's called de Sitter space, and we live in a space-time that there's some evidence, more than some evidence, a lot of evidence that it's tending towards something called de Sitter space. What is de Sitter space? It's an exponentially expanding space driven by what is called dark energy. And we don't understand the quantum mechanics of those kind of space-times. So I've been thinking about that on and off for 30 years. But in a focused way for the last 5 years.
So what are some of the problems with de Sitter space in string theory? Because it's primarily anti-de Sitter space.
That's correct. Anti-de Sitter, well, it begins with the so-called holographic principle that the world can be described by a theory that lives, so to speak, on the boundary of the space-time. That's the holographic principle. In this room, I'm sitting in a room now. The room is filled with stuff. The description of that stuff, ordinarily, the ordinary description of that stuff is that you have quantum fields in the room, you have particles in the room, you describe them in an ordinary way. In quantum gravity, we know now that the correct, precise description is in terms of a theory that lives on the walls of the room. And that's a little bit unusual, a little strange. It's called the holographic principle. It's widely accepted. While it was Tufte and myself who put it forward a long time ago, this is a widely accepted principle now, that there are enough degrees of freedom just on the boundary of the space to describe everything in that region of space. Anti-de Sitter space is a space that has a boundary And that boundary is very, very important to the description. It's where this holographic description takes place. We don't live in anti de Sitter space. Nothing like it. We live in something called de Sitter space. Now, you might get the feeling that de Sitter space and anti de Sitter space are almost the exact opposite of each other. Yeah, more or less. That's correct. So we live in the wrong kind of world to be described by theories of anti de Sitter space. We have to start over again. We have to start building theories that don't have boundaries, because de Sitter space does not have a boundary. Anti de Sitter space does. We have to start over again, and there's not a lot of people thinking about it.
Now, if our universe is de Sitter, why is it that not plenty of people are thinking about it?
Beats me. I don't know.
Well, one of the technical reasons in de Sitter spacetime, the boundary is time-like and at future infinity, and so holography is more difficult to formulate, whereas in anti-de Sitter spacetime, the boundary is space-like at spatial infinity.
In anti-de Sitter space, the boundary is the boundary of space. There is no boundary to space in de Sitter space. What you're probably thinking of is that there's a kind of boundary to time. But that's not the kind of boundary that the holographic principle envisions. So we need to start over. If you were an astronomer and you look out at the world, you would, to the furthest distances possible, you would discover that there is a kind of boundary. It's the horizon of your space. The horizon is not the kind of boundary that anti-de Sitter space has. So you're asking me to explain some very technical things. But let me just say that the world we live in is not the kind of world that the mathematics that we understand, the mathematics of anti-de Sitter space, is about. So we need to start over again, where the boundary of space is a horizon, not a boundary in the same sense. But you're asking me questions which are, I think, just too hard for me to explain.
So would there be a DS-CFT correspondence?
No.
Or only in extremely special cases?
No, in no case. In the sense of the usual holographic principle, where the boundary is a boundary of space, it most certainly is not a conformal field theory. CFT means conformal field theory, and that's exactly the wrong thing for de Sitter space. It's exactly the right thing for anti-de Sitter space. And we don't know what the right thing is for de Sitter space. So I've been experimenting around for a number of years with a simple model, trying to argue that it describes some kind of de Sitter space. I'm not sure my colleagues agree with me. But the bottom line is we know very, very little about it. So that raises a question that you asked: why isn't everybody thinking about it? Beats me. I don't know. You'll have to ask them. When I ask young people, they say it's too hard. And I say, well, come on, it's virgin territory. Anything that you manage to say about it will be new. Thinking about old things is very hard because almost everything has been said by somebody in the past. This is open territory. Just get into it. And they say, no, they're scared. They're scared. They might not get a job. They might not be able to make any progress. It's too hard. Yeah, they might be right. Maybe they won't get a job, but it's not the criterion for whether you should work on something in science. You should work on it because you're curious. You should work on it because it's relevant to the real world. Not, in my view, be afraid of it because you might not get a job.
So speaking of passion or curiosity, string theory has been a passion of yours for decades. How has your passion evolved?
Since 1969. How has my passion evolved? That's a psychological question, and I'm not a psychologist. Ask me a physics question.
How about this? How about I quote you from a podcast with Krauss? He said,
Okay.
describing string theory, look, string theory is supersymmetric. It fails when you don't make it supersymmetric. It has exactly a zero cosmological constant, has a slew of features that are different from the real world, and that you can tell Krauss with absolute certainty that string theory with a capital S is not the theory of what you'd call the real world. And I think you said, I can tell you this with 100% certainty. You being Krauss.
There's a precise, very precise mathematical structure called string theory. It's so precise mathematically that mathematicians have won Fields medals for contributions to it. Field medals. It's a very, very precise mathematical structure. It exists. It's well defined. But it has some features which the real world doesn't. As you said, supersymmetry, whatever supersymmetry is, special mathematical features that make it solvable and make it possible to calculate things in it. And we know for certain that the world that we live in does not have those special features. I call the very precise theory string theory with a capital S. Now, can string theory be expanded into new territory, which is not so very supersymmetric? We don't know. We don't have a generalization of string theory which is not supersymmetric. People talk about it all the time. They talk about breaking supersymmetry, blah, blah, blah. But there is no real theory of that. Maybe it exists. Maybe there exists a slightly expanded version of string theory, which is a little more general, which is not supersymmetric. But we don't have that. So I can tell you with certain, string theory with a capital S, the precise mathematical structure, which, as I said, mathematicians win prizes for. Incidentally, no physicist has ever won a big prize for string theory. I can tell you with absolute certainty that it is not the real world that we live in. So what do we make out of that? I don't know. We need to expand the theory. We need to generalize it a little bit. And in fact, I can say a little more, that no known version of it, no precise known version of it exists in de Sitter space. We live in de Sitter space. So we have a lot of work to do. And it takes not only great brilliance and great smartness and so forth, it takes some courage to move into areas which are so unknown that who knows, we might spend decades trying to unravel it. But that's where we have to go. I wish I could tell you, I see the way, look, I'm 84 years old. I'm not the one who's going to do this. It's going to be young people who will do it. And at the moment, I actually don't know any young people who are working on this.
Who are working on a generalization of string theory?
Yeah, a generalization of string theory, which is not dependent on these very special features, usually called supersymmetry, but they're just very special mathematical features that make the theory simple and easy to solve. Again, we don't live in that world, and I actually don't know anybody who is striving to try to expand the theory into either de Sitter space, which is not supersymmetric, or just more generally into an expanded version of the theory. And older people worked on it in the past. They worked on something called spontaneous breaking of supersymmetry. Don't worry about what it means. It just means the theory wouldn't be supersymmetric. And they failed. Now, that's not a criticism of them. I worked on it and I failed. That's not a criticism of anybody. But it's a fact that there is no precise theory which is not supersymmetric. That is intolerable in a sense. It can't stay that way We have to describe our world. That's our purpose. And as I said, I don't know anybody who's actually working on that. If you were to send out a message to all the world's theoretical physicists, is anybody working on a generalization of string theory, you'll probably find some yeses, probably mostly among older people. And somehow we have to change this.
The difficulty here comes from the elusive question of what defines string theory. This question was infamously posed by researchers at String 2023, and there was no uniform answer. Susskind's response frames string theory as any theory of quantum gravity. However, critics argue that quantum gravity is just one single approach to a theory that combines quantum mechanics with gravity. Furthermore, string theory is merely an example of a quantum gravity theory, not the example. There's loop quantum gravity, there's causal sets, for instance. At what point does redefining a theory by changing the capitalization from big S to little s become an example of wanting to have one's cake and eat it too? In other words, to claim success despite what even people in the field themselves call a failure. For more on this, see the talk by Edward Frankel. Critics liken this to if string theory as a field said, hey, my flying car prototype didn't work, but I'm not a flying car manufacturer with a capital F. I'm a successful flying car manufacturer with a lowercase f, because success to me now means any movement from point A to B, where bumps on the road momentarily lift you. And I can achieve that even by calling you an Uber. Oh, and by the way, I've changed my definitions while along the way systematically destroying the careers of anyone working on actual flying vehicles.
And somehow we have to change this.
Now, this is huge news, at least to myself, because you're one of the founders of string theory.
Yeah.
And string theory is one of the, if not the most dominant by far, actually, in theoretical physics.
Yeah.
For fundamental physics. And for one of the founders, the fathers, to come out.
Before you go ahead, let me tell you what the good news about string theory is. It's a mathematical theory which contains both general relativity and quantum mechanics. In that sense, it's an existence proof that quantum mechanics and gravity can coexist with each other. For many years, people thought that quantum mechanics and gravity were at each other's throats. They couldn't be reconciled. We know, on the basis of string theory in particular, let's call it anti-de Sitter-space string theory, we know with certainty now that quantum mechanics and gravity can coexist. Capital S string theory combines the two in a very beautiful way. We know, for example, with certainty, because of this supersymmetric theory, that black holes respect quantum mechanics. It was thought by Hawking for many years that quantum mechanics and black holes couldn't be reconciled, standard principles of quantum mechanics. We know that's false, and in that sense, we have an existence proof for the consistency of quantum mechanics and gravity. That's no small thing. That's a big thing. And that's mainly what string theory up till now has done for us. Apart from there's another thing that's done for us. In another form, string theory has described hadron physics. Hadron physics means protons, neutrons, and mesons. But it's a separate issue. String theory is a very fundamental theory, has done this one spectacular thing. It's given us an existence theorem that quantum mechanics and gravity can exist together. And as I said, that's no small thing. It's a major development in physics over the last 20, 25 years, maybe more. And so string theory in that sense is not a failure, but by no means is it a failure. It's a spectacular achievement. But it does not yet describe the real world. It has to be expanded. It has to be generalized. We don't know how.
What other approaches exist that reconcile general relativity with the standard model?
Well, the standard model. Sorry, this is not the question of reconciling general relativity with the standard model. You mean the standard model of particle physics or cosmology?
Right. Particle
physics. There is none. There are none. There simply are none. If there was one, we'd be working on it. That's the problem. String theory in some way looks a little bit like the standard model. It has fermions, particles, it can have, with the appropriate version of it. It can have electrons, it can have photons, maybe it can even have quarks, but always this supersymmetry gets in the way of comparing it with the real world. So in many ways, it does look like the real world, some versions of it. But in many ways, it doesn't look like the real world. So we'd like to find something that has the good features without the bad features. Still a work in progress. We can't do that yet. And is there anything else? Not to my knowledge. Not to my knowledge.
What about Latham Boyle and Garrett Lisi, or Peter White, or Eric Weinstein, or Julian Barbour, or Stephen Wolfram? They all have their own theories of everything.
Okay, I will ask you, what do you think of them?
Well, I can tell you what each of their theories are.
No, we don't have the time for that, obviously. I would love to know, but I know that Stephen Wolfram is a great advocate of little checkerboards. What do we call them?
Cellular automata, at least before, and now it's been generalized from graphs to hypergraphs.
Okay. That certainly doesn't contain either gravity or quantum mechanics. So it's a failure.
Well, Eric Weinstein's is that general relativity itself contains the ingredients of Petit Salam, along with the 3 generations and cosmological constant, which I could explain to you at another point.
I don't know who Eric Weinstein is. I don't know his theory, so I can't comment.
Do you know Julian Barbour or Latham Boyle?
Julian Barbour is the fellow who doesn't believe in time.
Yes, that's correct. That's correct. Yeah,
I believe in time. So, I think what he says is trivial. That the whole world, what does he call it? The block universe?
I believe it's shape dynamics.
Oh, then I don't know. I don't know.
Okay, here's something else you said that was super interesting. SU5 may at some level be correct. And I believe you then corrected yourself and said, well, or something that has SU5 as a subgroup.
Yeah.
So can you explain why you believe at some level that's correct? Because many people hear that who are physicists, and you can be technical, just so you know, and they hear that, they think, oh, grand unified theory, that's been disproven, proton decay. So in your mind, when you hear SU5, what are you thinking of?
When Glashow and Georgi put forward the SU5 theory, there was a spectacular way in which the ordinary particles, electrons, quarks, all the ordinary particles fit into SU5 multiplets. And it seems to me that's no accident. The way that the neutrinos, electrons, protons, the standard model fit into the SU5 in a very nice way, I feel is not an accident. Maybe it is an accident, but I feel it's not an accident. Now, their original SU5 theory was too simple, for sure. It was certainly too simple. People have generalized it, 010, 016, all kinds of things, but all of those things contain SU5. Mm-hmm. And the particles fit into the SU5 multiplets the way that in these other more extended theories, the particles still fit into the SU5 group in pretty much the way that Glashow and Georgi said. So I feel it's not an accident. I could be wrong. But the statement that baryon decay doesn't happen, I think that's premature. It's always kind of the case that people try to make their theories so that in the very next experiment, whatever it is they're looking for,
Right.
always, not always, many times, people will tailor their theories so that the next round of experiments will discover what they're looking for. That was true of supersymmetry. We know that supersymmetry is not an exact symmetry of the world. So for years, people made these theories in which an approximate supersymmetry would be discovered at the very, very next accelerator experiment with no good reason. No good reason. It's just they wanted it to be true. They wanted to discover it. I think the same is largely true with proton decay. That in fact, let's put it this way: over the last, how long has it been that proton decay ideas have been around? For almost 50 years, something like that. Experimentally, the upper bound on the lower bound on the lifetime of the proton has gone from about 10 to the minus 30, 10 to the 32 years to all of 10 to the 34 years, or 10 to the 33 and a half years. There hasn't been a huge change in the constraints from the time of the early George I. Glashow theory. So I think it's quite premature. If the proton decay occurred at 10 to the 35, with a lifetime of 10 to the 35 years, the 10 to the 35 years, whatever, we wouldn't know. We wouldn't know. So I think there's plenty of room in these theories for the proton to be stable at the current experimental limits and still be unstable the way SU5 needs it to be. But I'm guessing. I think people have just given up on that subject because they don't see ways of experimentally confirming it other than just wait. The proton decay is an interesting thing. The lifetime of a proton is known to be longer than about 10 to the 33 years, I guess. Okay. That's how then can you ever detect the proton to decay? You take a proton and you sit there and watch it for 10 to the 32 years, 33 years? No. What you do instead is you take 10 to the 32 protons, 33 protons, and you wait for one to decay out of all the huge number. It's an incredible thing that experiment can be done. Just think about it for a minute. How many protons is 10 to the 30? A huge number. And you sit there waiting for one to decay. And it's kind of a spectacular thing that's really at the edge of technology. And if the proton was a little more stable than that, instead of 10 to the 33 years, it was 10 to the 35 years, we would have no chance of discovering it for another, 50 years. So I think it's premature to say that proton decay has ruled out SU5. I think that's premature. But, it really doesn't matter what I think. We just have to sit and wait.
Can you talk about the landscape?
Yeah, yeah. String theory is a peculiar theory in which the behavior of space-time and so forth is not an input. It's an output of some equations, and those equations have many, many solutions. The meaning of that is that there are many possibilities within string theory for the coupling constants, for the masses, even for the particle spectrum itself, for the cosmological constant, for all the parameters of the theory. It's not a single theory of the universe in which the parameters all are necessarily fixed by the equations. Not at all. Instead, it's a theory that has many, many solutions to its equations, and those solutions each one of which has a particle spectrum. It has a collection of coupling constants and so forth. Again, I'm speaking about the precise version of the theory, string theory with a capital S. If we ever learn a theory which is an expanded version, it's very likely that that expanded version will have even more possibilities. How many possibilities? 10 to the, people always quote 10 to the 500 different possibilities. It's much more than that. And looking for the right version of the theory is very much looking for a needle in the haystack. That collection of theories, that collection of solutions of the theory is called the landscape. It's called the landscape by me, and it's just the collection of all possible solutions of string theory, of the equations, all the possible values of coupling constants, all possible values of the cosmological constant. And it's a huge, huge number, huge landscape. How we find a way around in it, even if we ignored the question of supersymmetry, even if we ignored that particular issue, there's just too many to sort through. What we do about it, I don't know. We've really reached some very, very difficult things in the physics of fundamental interactions and so forth. Experiments have gotten progressively harder. If you go back to the early parts of the 20th century, how long did it take to do a quantum mechanics experiment? A year, something like that, maybe even faster. Now, an experiment can easily take a whole scientific lifetime. You have to build a bigger accelerator, you have to build bigger detectors, you have to get the money to do it, and so forth and so on. So experiments from the beginning to the end can be 40 years or more, entire scientific lifetimes. And so we've run into the problem of the difficulty of experiment. We've also come, if this picture of string theory that has this wildly proliferating landscape of possibilities, if that's correct, then we've run into the obstacle of just too many things to sort. So things are hard. For that reason, many of my colleagues, myself included, said, let's put that on the back burner. Let's simply focus on the consistency of quantum mechanics and gravity. We know gravity exists. There's no question about that. And we have to be able to put it into our quantum theories. We have to be able to make it mesh with our quantum theories. And so most of the work that people like myself, people that I interact with on a daily basis, is about the connection between quantum mechanics and gravity. And theoretical constructions, theoretical models that contain both gravity and quantum mechanics. If they contain gravity, they will contain black holes. Hopefully, we'll be able to answer some of the paradoxes about black holes. But obviously, that's not completely satisfactory. We do want to have a theory which describes the real world of electrons, photons, protons, neutrons, and we're far from it. I think we're very far from it.
So, is there a reason to believe that with any of the possible solutions to the string theory landscape that there should be an associated universe to it? So I'll give you an example. With Einstein's equations, there are a variety of solutions. You can even have a neutron star with a hollow center, technically. It's not like we think there must be a universe that corresponds to every solution of Einstein's equations.
If the universe is big enough, maybe so. Maybe if the universe is really big enough, then no matter how unlikely something is, it will occur somewhere. If the probability of something is 10 to the minus 100, but the universe is big enough to have 10 to the 200 regions of space, then you have more than enough to somewheres find your hollow neutron star.
You understand the point that just because
I don't.
there's the laws of physics that allow for something, it doesn't necessarily mean that the existence has to follow that possibility.
I qualified my statement. If the universe is big enough, if it's big enough and if its equations, first of all, a question, do its equations allow variety to exist? Do the equations allow a region over here and a region over here to be different from each other? Which the equations of cosmology, inflation, eternal inflation do allow, that the universe can have patches with different behaviors. And if the universe is big enough, then just on ordinary probability grounds, some place will have whatever it is you're looking for. Now, you're not used to thinking of things which are that big, so big that essentially anything can happen somewhere. You're not used to that. But that's what it would take to make this landscape theory and all that kind of stuff make sense. The universe just has to be very big. To our knowledge, the universe is exponentially expanding. It may have been exponentially expanding way, way into the past. If it was exponentially expanding deep into the past, it will be exponentially big. And what is exponentially big? It means very, very much bigger than the region we can see. We're used to thinking of the universe as being about 20 billion light years big. But that's just the part we can see. That's the part that we can see without running into a horizon. If the universe is old enough and exponentially expanded for a long enough time in the past, it could be vastly, vastly bigger than that.
Well, what I mean is that Einstein's field equations allow for the Schwarzschild solution, for instance, so static black hole. That static black hole is eternal, it's isolated, it doesn't decay, it doesn't even form. It's always been there and it will always be there. So that can't be a solution of the universe, no matter how large the universe is spatially. In other words, GR is about the whole universe itself, and that any particular solution, sure, you could say it's true in an isolated case, but if you take a solution seriously, it's about all of space-time.
Yes, Einstein's equations by themselves would say that a black hole will just sit there forever and ever in otherwise empty space. Hawking told us no. Yes, Einstein's equations are wrong about that. The black hole will evaporate. But I'm not sure that's relevant to our discussion here. Einstein's equations predict that a black hole is eternal. Quantum mechanics predicts that a black hole will evaporate. Which one is right? Almost everybody I know thinks that the quantum mechanics answer is right. But that's beside the point. We're not talking about black holes here. We're talking about what a physicist would call vacuum solutions.
Mm-hmm.
Vacuum solutions mean essentially empty space. When I say there's lots of solutions, I don't mean that the solutions describing black holes. I mean that are solutions describing empty space. And what are those solutions about? They're not about the presence of black holes. They're about the values of the coupling constants, about the values of the masses, about the spectrum of elementary particles. So each solution has a different collection of elementary particles. Some may have electrons which are 2,000 times lighter than the proton. Somewhere else in the space of solutions, you might have electrons which are 2,000 times heavier than the proton and neutron. That doesn't describe our world, but nevertheless, there may be many, many solutions like that. Some of the solutions may have large cosmological constants and not coexist with what we know. And some small fraction of them may have very, very small cosmological constants. We're not talking about the presence of black holes. We're talking about what empty space is like, what the rules of quantum field theory will look like. And as I said, there's a huge variety of those things. Now, your question is a good one now. Do we have any reason to believe that these different solutions will materialize and manifest themselves in our large universe? Is the universe big enough so that statistically all of these different properties will exist someplace in some region of space? Inflation is a theory which tells us that the universe is maybe exponentially, and maybe even exponential, maybe even exponential times bigger than the region we can see. So we have no idea what's out there beyond the region we can see. It could be a bit of this, someplace someplace else, and that's what the equations tell us. The equations tell us that if you wait long enough and the universe gets sufficiently big, it will be filled like a patchwork quilt with regions of different properties. Some with small cosmological constant, some with big cosmological constant. And, there's just be a lot of stuff out there.
So about inflation, Penrose and Steinhardt, they believe that inflation doesn't solve the fine-tuning problem. So Penrose, I believe, says that it just pushes the problem back about extremely specific initial conditions. What arguments against inflation do you find to be the most credible, or the ones that are the most challenging to you?
No, I don't. I think it's still possible that inflation could be wrong, but there's so much good confirmation, observational confirmation for it, that it seems to me very unlikely that it's wrong. Look, there are still people who believe in the flat Earth, for God's sakes. There's people who believe all kinds of weird stuff. Don't think about individuals. Think about the consensus of the largest fraction of physicists working on these things, and you'll probably be right. The overall consensus of the field tends to be right. The peculiar individuals, no matter how famous they are, no matter how brilliant they are, if they're off that consensus, and they've been off that consensus for a long time, they're probably wrong. That doesn't mean for sure that they're wrong. But don't look for the weirdos. Look for what the consensus of, the majority of well-respected, highly accomplished physicists believe. And you'll probably be right. They'll probably be right. There's no guarantee of it. There are very few cases where the consensus has gone wrong for a long period of time, just where some offbeat idea of some particular individual suddenly changes everything. I'm not saying it doesn't happen, but rarely. So Penrose, what can I say? He believes all kinds of things that I wouldn't subscribe to. But more than that, things that the consensus wouldn't subscribe to. Steinhardt, I don't know what drives him. He seems to have a problem with inflation. I don't know why. Go to the observational cosmologists who actually measure these things. I think almost all of them will tell you that there's strong evidence for inflation, experimental evidence for it, observational evidence, in the form of fluctuation spectrum, the spectrum that's necessary to describe evolution of structure and so forth. Highly successful theory. As I said, the consensus is that it's correct, and they're probably right.
Look, Professor, we can't make an appeal to consensus.
No, we can't.
So, firstly, that's a logical fallacy. I know you know that. And I don't think much science could be done, let alone physics could be done, if we were going to make such appeals. And sure, we can make probabilistic arguments, but your own unconventional views would have been squashed from the starting line if people pointed out that they're probably incorrect as an argument against them. And by the way, Penrose isn't just an offbeat no one. This consensus that you mentioned in theoretical physics, forget about experimental physics, though that's a great point in experimental physics. In the theoretical end, we've already agreed that it's primarily string theorists, which means you're going to get a biased set as a response for anything that has to do with consensus in theoretical physics. The proportion of people who believe in inflation from string theory versus those who don't, there's a disparity there.
Yes.
Even if it's the case that, string theory is not predicated on inflation nor vice versa.
Yeah, I would say most of the string theorists I know, not completely. I think Kumran Vatha sits on the fence about it. But
Gross also believes that inflation, or at least the multiverse that comes from inflation, is of a different sort of not experimentally accessible or unfalsifiable hypothesis, because it's an in principle unfalsifiable hypothesis, unlike atoms of the past, when in principle you could verify atoms with enough precision. But David Gross says that he doesn't like the multiverse.
400 BC, when the atomic theory was first put forward, that was exactly the complaint against it. This is unverifiable. They're too small. We'll never be able to see them. So when quark theory came out, everybody said, quarks are confined. We'll never be able to see them. They're unverifiable. What's unverifiable at one time becomes verifiable when technology improves to the point where it can be seen. So will we be able to do the kind of ultra-precise experiments that might be able to detect some things about eternal inflation? Maybe. An example, the flatness or the non-flatness of space, not space-time, but space. Eternal or the current theories of landscapes and Coleman-Delucia instantons, whatever, the picture of this landscape filling up with lots of stuff has a prediction. It predicts that space is negatively curved as opposed to positively curved. At the present time, I think to about 1%, we know that space is flat. That's kind of like saying the Earth is flat, because if we look only at a small region within a couple of miles of where we are, it'll look very flat. But if we look out further, in particular, if we look out past the horizon, what Christopher Columbus was supposed to have looked at. He looked out at the sea and to the horizon, look out a little past that. If he could, maybe just get high up on a ladder and see a little further, he would discover that the Earth was round, positively curved. The same thing here. If we can do better experiments, we may discover that space is curved. Not locally, but globally. If the space came out to be positively curved, that would be a direct refutation of, let's call it this landscape theory, or this eternal inflation theory. If it comes out to be negatively curved, it will not prove that these theories are right, but it will prove, but it will be consistent with that. So to say that they're unverifiable is just wrong. We just haven't been able to do the high precision experiments to measure the curvature yet. And another possibility is these different worlds with different values of the constants, they can actually collide with each other. One possibility is that hidden in the details of the CMB, of the cosmic microwave background, we might see little patches which look like collisions with other regions. These are something that in principle might be detectable. So to say that it's unverifiable But something can be unverifiable within the current technology and still be true. In fact, it's even possible that it could be unverifiable to all technology that we're ever likely to be able to produce and still be true.
Exactly.
Yeah. So, in which case, we'll be left only with mathematical consistency, theoretical consistency, conceptual consistency, and that is how we'll have to evaluate these theories in the end.
Yeah, Nima Arkani Hamed says, okay, if you're trying to examine the Planck length, then you're going to put so much energy into it that you're going to then create a black hole, and you're going to start to create more and more of that black hole as you put more energy into it. So short lengths become long lengths. But then
it wasn't
that's
Nima
not a...
Hamed who said that. It was Tuchman and myself.
Okay.
Nima is quoting me.
Okay, great. Okay, so you said this. So this is not an argument, though, against the existence of something at the Planck length. It's against an argument of us probing it, correct? Or no? I'm riffing off of what you just said.
If something is really absolutely in principle unprobable, you might begin to wonder whether it means anything. Whether your theories, which are calculating things in some region which is fundamentally unprobable, whether they mean anything. Now, an example would be the uncertainty principle. You could say the uncertainty principle is a limitation on, the same kind of thing. You could say it's a limitation on what we can probe, but it doesn't seem to be a limitation of the devices that we have. It seems to be in principle that we can't. I think that the same is likely to be true here. That likely to be a fundamental limitation. So fundamental, not just that you don't have the technology to do it, but no possible technology can see things. You're asking whether you can see things smaller than the Planck length.
I'm just asking whether or not something at the Planck length exists, is independent of the probing of it.
Planck length, yes. But it's smaller than the Planck length, I suspect, no. Yeah. I mean, how do you probe small distances? You probe small distances with high energy. The higher the energy in 20th century physics, the higher the energy, the smaller the distances you probe. As you said, that as you try to probe even smaller and smaller distances, the energies necessary in a collision become so large that black holes form. And not just black holes form, the higher the energy, the bigger the black holes. So you come to a fundamental limitation on how small you can detect things. But it's not just a technological limitation, it's a very fundamental limitation. And I would say 21st century physics, at least among the people that subscribe to these ideas, is that as you try to probe smaller and smaller with higher and higher energies, you will come to a point, the Planck point, which is sort of a minimum length you can see. And then as you go even higher in energy and higher in energy, you will be probing again the bigger lengths. And but different properties of the bigger lengths than you probed before. So yeah, what Nima says, I think, is a standard, by now, the standard picture of what can be probed. And not just what can be probed, but that the limits of probing really define or should be built into the theory. If you really have a fundamental limit on what can be probed, you might say, my theory should not produce answers for things which are totally unprobable. But, that's a prejudice. It may be wrong.
Well, wouldn't any theory have limitations on what it can't ask questions about just by definition? Like if you can't ask a question about it within the framework of the theory, then it can't answer it, no?
And maybe it shouldn't have, maybe the theory should be reformulated so that it doesn't have answers for those questions which in some sense are meaningless. The same Same issue happened with quantum mechanics. People tried and tried and tried to build theories in which, at some fundamental level, the uncertainty principle wasn't correct. That you could beat the uncertainty principle, even just conceptually, if not in an experiment. Ultimately, that's not the way things played out. The way things played out is that we believe that quantum mechanics not only does not have answers to these questions about that violate the uncertainty principle, but that quantum mechanics is constructed in such a way that those things don't mean anything. Those things don't have real meaning. The position and the velocity of a particle at the same time. So, one view is, well, the position and the velocity both exist at the same time, but we can't measure them. The other view is that quantum mechanics just doesn't allow you to even think of the position and the velocity at the same time. I think this latter view of quantum mechanics is the accepted view of quantum mechanics now. So it remains to be seen, but I think the same thing will be true of probing distances on smaller scales of the Planck length. That's my feeling. But I'm an old man, and the younger people will decide these things probably long after I'm dead.
What is it that you look for in a student?
Oh, me personally?
Yeah. What is it that you look for?
Somebody that I can interact with in a more or less equal way. Somebody that is not totally dependent on me for what they're doing, and who can interact with me in pretty much the same way as a colleague would interact with me. And somebody that I don't have to be afraid of walking on eggs, that I can tell them, no, you're wrong, without having them freak out and go home.
Oh.
And somebody who could, even more so, somebody who can tell me I'm wrong. That's very, look, anybody could tell me I'm wrong, but somebody who can tell me that I'm wrong with good reason and not be afraid to say so. Somebody who has their own thoughts, somebody who's not dependent on me to give them a problem, and who can interact with me on a more or less equal footing. That's what I look for. Yeah, they do have important and interesting things to say. I remember I had one student a long time ago who would come to me and ask me a question, and I would say, go away. He'd come to me and tell me something, I'd say, go away. But after a while, I began to realize that his questions were not only good questions, but I didn't know the answers, and that he sometimes knew more answers than I did. It happened to be a he in this particular case, happened also with a she. And I said, wait a minute, maybe this person is the kind of person I can interact with. And so I'm not an easy person for a student to deal with, by the way.
Why?
Because I demand of them that they do something that most students can't do. That's interact with me on an equal basis, tell me I'm wrong when I'm wrong, not be afraid of being told they're wrong, and not have to walk on eggs with them. Many people think you have to be very careful with students, not to discourage. I just deal with them as though they were colleagues.
From the get-go, not over time.
From the get-go. Pretty much.
So I recall you said that when you were growing up, when you were a graduate student, you would be irreverent. You would look at your professors like, these people don't know what they're talking about. Sure, you had respect for them.
Where did I say?
No, just let me finish. You'll see where this is going. Said something like this. And that now students come to you and ask you, what are the problems I should be working on? And now these are not the sorts of students that you want to interact with, like you mentioned. But I recall you saying this.
Yes, I don't mind if a student came to me and said, what should I be working on? What's important? No, that's perfectly fair game. I don't want a student who is dependent on me to tell them what's important. I don't want dependency of the kind that here's a problem, go home and do it. When you finish with it, come back and tell me what the solution is. That's not my style. My style is to interact with the students that I have as equals. Now, a perfectly good equal can come to me and say, "Hey, Lenny, what do you think the important problems are?" And I might say to them, "Oh, Fred, I don't have a friend named Fred, but Fred, what do you think the important problems are?" When we get into a discussion, that's fine. So, no, I don't mind somebody coming to me and asking me what I think is important. What I do mind is them being totally dependent. Not mine, but that's what I don't deal with well. And it's a limitation of mine. It's a limitation of mine that I can't deal with students that are too dependent on me intellectually. I don't know what to tell them. A student comes to me and said, "Give me a problem." I said, "If I had a problem, I would solve it. And if I solved it, I would publish it." So, but let's talk about what the problems are, and let's see if together we can solve some of them. I guess that's the bottom. I want to be able to deal with people and say, let's talk about what we think is important. I'll tell you what I think is important. You tell me what you think is important, and together we'll solve some of these problems.
In physics, there's a push for quantum information in the past 10 years or so.
Right.
And from that, EPR equals ER came about, and complexity equals volume.
Yes.
Can you explain those? Is one a generalization of the other?
Oh, boy. Yes, I can explain them. It would take about 3 hours. I'm not going to try. No. ER equals EPR is a very interesting development. It originated the two papers of Einstein, both in the year 1935, which had nothing apparent to do with each other. One of them being solutions of Einstein's field equations, which had wormholes connecting, in modern language, wormholes connecting two distant black holes. Einstein, I don't know if he thought about it that way, but today we would say the Einstein-Rosen bridge is a solution of general relativity with two black holes connected by what we sometimes call the wormhole. That was the same year, exactly the same year, was Einstein's paper with also Rosen and Podolsky, where they, I think, first put forward the ideas of entanglement, quantum entanglement. He said nothing to do with each other, as far as Einstein knew, I suspect. I do not think he saw somehow deeply that they were connected with each other. I think it's accidental that they both occurred the same year. But what we now know is that when two black holes are entangled, quantum mechanically entangled, they will contain an Einstein-Rosen bridge or a wormhole between them. That wormholes and entanglement are the same thing. So that was, I think, a very dramatic development in the last more than 10 years. That was, 11 years ago, something like that. The holographic principle was a very powerful principle about quantum information and gravity. What else did you ask? Yes.
Complexity.
Yeah.
Volume.
Things come to thermal equilibrium. Isolated systems, particles in a box, a sealed off box, or just systems otherwise isolated from other systems, they come to thermal equilibrium in time. And the time for things to come to thermal equilibrium is very rapid. Doesn't take long. Long on what scale, don't worry about it, but you see things come to thermal equilibrium pretty quickly. Now, a black hole is a system which is in thermal equilibrium. And if you think about how long it takes from the time that black hole is first created, when its horizon is first created, how long does it come to thermal equilibrium? Very fast. And from the general relativity point of view, it's just that the area of the horizon very quickly settles down, starts out very small, area starts out a tiny little area and expands, and then stops expanding. And that's when it comes to thermal equilibrium. That, if you take the case of a solar mass black hole, a solar mass black hole would come to thermal equilibrium in less than a millisecond. If you did something to the black hole which kicked it way out of thermal equilibrium, it would come back to thermal equilibrium in somewhere between a micro and a millisecond. So very fast things come to thermal equilibrium. On the other hand, if you look at Einstein's equations and you ask not how the area of the horizon grows, that's one feature, but you ask how the volume of the interior of the black hole grows, it grows for an exponentially long time, a huge amount of time. So the question was, what is it that's growing in the interior of the black hole? What information theoretic quantity, what quantity is growing? In the case of the area of the black hole that comes to thermal equilibrium quickly, it was the entropy of the black hole. Something else continues to grow for a very long time. We've known that just from Einstein's field equations. What is that thing? The only known thing that continues to grow long after a thing comes to thermal equilibrium is what's called complexity, quantum computational complexity. And that takes a huge amount of time, exponentially long for it to settle down. So I guess I put forward the idea that this long time growth of the interior of the black hole, which can't be seen from the outside, that long time growth was the growth of quantum computational complexity. And quantum computational complexity is a very subtle quantity. It's a quantity that quantum computer scientists know about. It was a property that I don't think any except for one or two people that I knew had ever even thought about or even heard about. I can tell you in a minute what complexity means, but this was not part of a theoretical physicist's tools. So when I put it forward, it very quickly caught on. It was not one of these things where it took a long time for people to realize that it might be right. And it caught on, and people learned what complexity is. Now, every single person who's interested in quantum mechanics and gravity has become probably more expert than I am on what what quantum complexity means. So I'll tell you what complexity means. It comes out of computer science. It's a question of how long it takes for a system to achieve whatever state you're interested in, some target state. You would like it to get into some state, starting with some simple state. By simple operations mean operations that only involve individually small number of degrees of freedom. If we were talking about a quantum computer, we would be talking about operations which only involve a small number of qubits at a time. It could be just pairs of qubits. Gates, the word is a gate. A gate is an operation which takes place on a small number of degrees of freedom. How many gates does it take to achieve a certain state? The minimum number of gates that you can use to achieve a certain state. That minimum number is called the complexity of the state. Now, complexity can continue to increase in quantum mechanics for a very, very long time, exponentially long time. In classical physics, it's not true. In classical physics, complexity saturates about the same time as thermal equilibrium comes about. In quantum mechanics, this was something Feynman realized. It was his explanation about why quantum mechanics is so hard, because there are just so many states to wade through, and quantum complexity can be vastly larger than what can be achieved in a reasonable amount of time. So the only thing that I could think of that this growing interior of the black hole could be connected to was quantum complexity. And I made some arguments, I gave some examples, I tested it out in various properties of complexity versus properties of black holes, and they matched. This was a surprise to most black hole physicists. They'd never heard of complexity for the most part. I think the only people that I know that even knew what complexity meant were my colleague Patrick Hayden, who is actually a computer scientist in addition to being a physicist, and one of my students, Dan Harlow. They knew what complexity was, and in fact, to some extent, they even taught me what complexity was. To my knowledge, those are the only two physicists that I had ever heard of who knew what complexity was. Now everybody knows what it is. So yes, it does appear that the growth of the interior of black holes is the growth of computational complexity. The state of the black hole gets more and more and more complex for a long, long period, much longer than it takes for it to come to thermal equilibrium. And that was a surprise. Anyway, I think without a blackboard and without some technical discussion, I think I've told you what I can tell you about complexity and ER equals EPR.
You mentioned 't Hooft, you mentioned entropy. So there are two questions I have, and you can choose to answer both or just one of them.
Yeah.
I believe it was I believe it was von Neumann who said no one understands entropy. Do you still think that's true? So that's one question about entropy you could tackle if you like.
I don't know. Did von Neumann say that?
He said that if you don't know what you're talking about, you can call whatever you're talking about some adjective then entropy, like von Neumann entropy or Shannon entropy, because no one knows what entropy is anyhow.
Or Boltzmann entropy.
Yeah. So there's that. And then there's also, what do you make of that? Do you feel like that's overrated? Entropy is understood?
Yeah, I think look, nothing in physics tends to be ultimately understood. We always have developing understandings of almost everything. So to say that something is understood, if you mean by that a final, complete understanding that will never change, I think almost nothing in physics is like that. But if you mean there's a working consensus on how to use it, forget the word understanding for a minute. How to use it, how to make predictions with it, how to use it. I think there's consensus about what entropy is.
What could be more
Yes, I thought I understood.
About,
you're telling me something now that you're telling me that von Neumann didn't think he understood it. Well, I'm surprised. I thought he understood it. I think I understand it. But, will it change? Will it be an evolution of our ideas of entropy? I think probably yes.
The definition of entropy has to do with counting microstates. However, there are other ways of viewing what entropy is. How do you view what entropy is?
It's one way of thinking about it. The other way I like to think about it is it's hidden information. That information about a system, detailed information about a system, which is for one reason or another hidden from you. Now, why would it be hidden? In the case of a gas of particles, what is the total amount of information that you need to be able to describe, I'm talking about classical particles now. What do you need to know about all of those particles to be able to predict their future? You need to know the position and the velocity of every particle. That's obviously not feasible. Why? Because there are just too many particles and they're too small. Too many and too small. So that information is hidden from you. It's hidden from you just by the fact that there are so many of them and they're so small, and you can't. No feasible experiment can determine the position and velocity of every particle. So all of that information is hidden. It could be hidden for other reasons. It could be in some other room where you don't even know where it is. But hidden information is what's called entropy. That's one view of entropy. The other is that it's counting microstates. Now, it's sort of the same thing. The microstates mean, well, what is a microstate? A microstate, in the case that I described, is the position and velocity of every particle. You count the number of microstates that you can't distinguish because there are too many particles, too small. You take all of those microstates, which you cannot distinguish from one another, and take the logarithm of that number, and that's the entropy. So ultimately, it's hidden information that you don't have the capacity to distinguish for one reason or another. As I said, another reason you might not be able to distinguish it is because they're hidden behind the horizon of a black hole, all of this information. So microstates is one view of it. Hidden information is another view of it, but they're really the same.
Right. What do you suspect the missing pieces to quantum gravity that your colleagues think differently than you about? Like, what do you suspect is...
I don't know that we think terribly differently. That's a very good question. I don't really think I have a clear answer, but at the present time, I'm very, very dissatisfied with our dependence, our complete dependence on anti-de Sitter space for understanding. That's where we understand the most. Anti-de Sitter space is kind of space that has a boundary where we have a very precise set of notions, and we simply have no corresponding understanding of the real world, which means de Sitter space. So I don't know exactly. I'm not even yeah, I think there are certainly big things missing, but this is one big thing that's missing, which I think we can focus on. What is missing? I don't know. I think if I knew what was missing, I would work on it. And yeah, it's not clear what's missing, but that's at least one which is definitely missing.
It could also be there's something that you suspect, the probability may be low, and even if it was correct, it would be too difficult for you to pursue currently. So that could be another reason you don't want to.
Yeah, absolutely. Another similar question is what's missing out of our understanding of quantum mechanics. Just why? Almost everybody that I've ever known that I thought deeply tell you we know how to use quantum mechanics, but the basic meaning of quantum mechanics is not understood at all. I would subscribe to that. And I know my friend Feynman believed that he knew how to use quantum mechanics, but he didn't understand. In fact, what he said was quantum mechanics is so confusing that I can't even tell if there's a problem about the foundations of quantum mechanics. Certainly, Einstein, of course, had problems with quantum mechanics. And pretty much everybody I know will tell you that the foundations of quantum mechanics, ultimate meaning, is really not understood. There's all these crazy theories like many worlds theories and other things that don't make a lot of sense to me, but are very, very confusing. And I really think we don't understand quantum mechanics at its deepest level. Okay, what's the problem? I think the problem is that when we think about a quantum mechanical experiment, we separate the world into the system that we're studying, which might be all of the rest of the world, and the apparatus or the observer. We separate them, and we don't think of the apparatus and observer as part of the system. We think of it as something which can interact with the system, but not as part of the system. We separate the world in that way. And that's essential for the way we use quantum mechanics. It's essential to make that separation. On the other hand, the detectors, the observers really are part of the system. We need to be able to describe in a single way both the system we're operating on, that we're studying, and the observers and the detectors. And furthermore, there can be multiple observers. Maybe there are even branches of the wave functions where there are no observers. So I think it's a separation into observers and system, which is artificial. It's not really part of the world. The real world is, everything is described by one set of principles and equations. The observers, the detectors are all, and the system we're studying, all part of the same system. And when we use quantum mechanics, we almost invariably make a separation into two distinct things. That's why we have this problem about collapse of the wave function. It's not collapse of the wave function. It's our detectors becoming entangled with the system we're studying. And I don't think we understand that yet. I don't feel I understand.
Yeah. Well, the many worlds people, you don't understand them or you don't think they're on the right track?
I have questions about it which they can never answer. It's a technical questions. There may be some truth to it. I don't understand it. No.
What are the technical questions that you put up to the many worlds proponents that they are unable to respond to?
Well, first of all, there's this picture of branching pieces of the wave function, which branch and branch and branch, and you know the way a tree grows. If you go upward from the trunk, the trees grow, but the branches never come back together again. Okay, that's the picture of the branching universe according to the many worlds idea. The universe is branches and branches. It's a probability tree. It's a decision tree.
Mm-hmm.
Keeps growing. Well, that's not correct. There's no question that the principles of quantum mechanics do allow the branches to grow back together again. And so that's one factor that they're using the wrong mathematics to describe this branching tree of possibilities. And the other is a technical problem.
The measure problem?
Yeah, there's a measure problem, but the question is how many branches emerge from each decision? From each decision, how many branches emerge? You usually think two decisions. It was this thing or the other thing. But that's not correct. If the probabilities for two things to happen are half and a half, then you can imagine the universe splits into two parts. What if they're a quarter and three quarters? Do you require that the universe splits into four parts, one of which does one thing, three of which do the other thing? What if it's some irrational number, the relative probabilities? Then the universe at each node has to split into an infinite number of parts in order to accommodate irrational numbers. So there are technical problems, and I don't dismiss the idea. I just say I don't think it's understood. My friend de Tuft dismisses the idea completely, and he may be right. I don't know.
Tuft is someone who you respect greatly and you think is an original thinker. And he has his deterministic, super deterministic quantum mechanics.
Right.
What is your opinion on that?
I understand where he's coming from. I understand the question he's trying to address. I don't think I can dismiss what he says. His very super deterministic view of things. Most of the people I know dismiss it. They think he's gone a little crazy. I don't. But I think it's wrong.
For reasons.
But I don't know what's right. So what use is there in saying I think he's wrong if I don't tell you at the same time what I think? That's like the string theorists. I'm not the string theorists. The critics of string theory who say bad, 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 bad. It's not confirmable, but they don't give you any positive idea of what might be right. Here, in criticizing both the many worlds and Tuft, which is the opposite extreme, I don't have anything to offer which is any better. So, which line of thinking, which of these two almost diametrically opposed lines of thinking may lead to some new and interesting way of thinking about things? I can't say. So it's almost useless for me to say or for you to listen to me. And when I say I don't, I'm skeptical about it.
Well, respectfully, Professor, we can't claim that there are no other contenders to string theory that are of quality if we don't examine the competitors.
But I don't know any competitors.
I brought some up to you, like Peter White or Garrett Lisi or Latham Neil Turok.
What is Peter White? If you look on the internet, if you look on the archive, he has a small number of papers which are bad. They're bad mathematics and bad physics. They're just bad. I probably shouldn't say that. I probably shouldn't, but I'm going to say it anyway. He has nothing to prefer at all. I assure you that if he had something that was compelling and interesting and that solved some problem, the physics community would notice it. I looked at his papers. I was unimpressed, very unimpressed. Lisi, I can't understand. I can't understand what he's doing. It's all dependent on some fancy mathematics that I don't understand. But I'm just being negative about these people. Maybe I shouldn't be. Who knows? Maybe they have something. Personally, I found it very uninspiring, what I've seen of their papers. So to think of them as competitors of I don't think. Loop gravity is another one. Loop gravity, I think, is better motivated. Incidentally, do either of these people, Lisi or Void, do they have anything to say about gravity?
Yes, Peter White does.
What is he saying?
So he has something called Euclidean twistor unification. And the Euclidean space-time rotations become an internal, so SO4 becomes SU2 cross SU2 under Wick rotation. And so that's some gravity-weak unification. And Lisi as well has gravity embedded with something that has the SU3 cross SU2 cross U1 as a supergroup, so a subgroup, sorry. So he has a supergroup.
Where's the gravity in an SU3 cross SU2 cross U1? SU3 cross U2 cross U1 is the symmetry group of the...
I understand.
I know you understand. Standard model of particle physics, excluding gravity, does not address gravity. So how does this address gravity?
He has SO1, 3 as well in there. And then as far as I know, the metric of space-time is the Cartan killing form of E8, but it may have changed. Doesn't matter, that's what it was at one point.
Whatever that means.
And he also has triality with E8. So he has an explanation for the 3 fermions. Now, the reason why I say this is because...
Yep. Has nothing to do with gravity.
No, not the 3 fermions. No, I mean, I'm not suggesting that the 3 generations have something to do with gravity. Although it could. I mean, who knows? But that's not what Lisi is saying.
I think you have to dismiss what I say about these people because I have not studied what they said in detail. it is possible that somebody who is offbeat, and when I say offbeat, I mean not part of the standard consensus, might be thinking something that is much deeper and smarter than I think. It is quite possible. Maybe it's one of these two people. I don't know. So far, I would say that I haven't seen anything which sparks any interest in me. That's all I can say. Loop
Sure.
gravity, a little more interesting. It was based on some ideas which at one time I thought might be interesting. But it doesn't seem to have gone anywhere. It seems to be petering out, doesn't seem to have any great success. I wouldn't be totally surprised if we discovered that some features of string theory and so forth are consistent with some ideas from loop gravity. I think that's possible. So it's possible. I studied it. Incidentally, I studied it many years ago. I was interested in it. It didn't seem to go anywhere. It just seemed to peter out and end up nowheres. But that could change. But you're perfectly right. We should certainly be on the lookout for ideas which are not the consensus. We should be watching for them and not immediately dismiss them because they're not exactly the same as the ideas that we've been pursuing. For sure, we should be doing that. So I would agree with you about that. And maybe we haven't been diligent enough with some of these ideas.
That's huge of you to say.
Oh, sure. Yeah.
I mean, that's commendable.
Thank you. That being said, I don't know any at the present time that I find compelling.
No, I think you should linger on that because I do think that's extremely large of you to say. I've spoken to several other people who are part of whatever this consensus is that's being referred to here, some string theory and so on. And many of them have a derisive attitude toward not only loop quantum, which you did not just now display that, although you don't think it's on the right track. It's not as if you're thinking that it's illegitimate in some manner.
No, I don't think it's illegitimate.
No.
I think there are claims. I separate two things. I believe there are claims that were made which were illegitimate. Claims to be able to do this or that, which don't hold water. But the basic ideas, I think, are legitimate.
I'm not done complimenting you.
Okay.
Colleagues like Sean Carroll, they...
Mm-hmm. But Sean Carroll is not one of the people who...
No, he's not a string theorist, but he defends string theory as if he's one of them.
Yeah.
It's almost like the Stockholm syndrome.
I don't think there's anything wrong with naming people because their views are, first of all, their views are widely known. And second of all, it's important to get their views out there.
Yeah.
So, yeah, look, you're right. Most of the people I know, and that might even include myself to some extent, are a little bit are derisive about a lot of these ideas. And you're correct that there is a very strong skepticism about them, and maybe to some extent unfounded. We all know that there's nothing hidden about that. The answer is I've looked at them and I don't find anything compelling about them. If you call that derision, yeah, I am a little bit derisive. However, I would say maybe there are elements in those theories which will come back in some different form, which will connect better with the things which I think are right. And that's a possibility, which I suspect most of my friends don't entertain. Anyway, that's I think I've exhausted everything I can tell you.
Okay, then let's just end with what advice do you have for new people, new students entering the field? There are many researchers who watch this podcast and many people who are excited to go into physics and philosophy. And even though you're not a philosopher, but let's just stick with math and physics.
Yeah.
Maybe even just physics.
First of all, the primary thing I would tell people is don't listen to older people. Well, listen to them. But if you think you know something or you think something is interesting and your older colleagues or your older teachers and so forth tell you it's uninteresting, it's wrong, and so forth, but you think there's some reason to think it's right, don't be intimidated by that. I have had the unfortunate experience of telling young people that I thought something was wrong and having them abandon it just before it became important. I was wrong. They were right. They listened to me and lost the opportunity to do something very impactful because they did listen to me. So my advice is, first of all, don't listen to people when they say something is wrong or impossible if you think you have good reason to think it's right. That's the first thing I would, and possibly the most important thing I would say. What you should work on, I don't know, because if I knew what to work on, I would work on it myself. So think for yourself. Don't pay any attention to people who say something is impossible if you think it's possible. And that's my main. And be curious. Well, don't be afraid. Don't be afraid. Follow your curiosity. If your curiosity goes in some other direction than the direction that the current consensus is pursuing, don't be afraid to pursue it. Even though it potentially could, people worry about damaging their career by working on the wrong things. The wrong things being the things that their elders and their more well-known colleagues are not working on. They feel if they want to get into physics for a job, so forth, they have to work on the things that are currently being pursued. Even if they know and understand that other things may be more important. So think for yourself. Think for yourself and don't be afraid to pursue it and follow your curiosity. That's my. And if you don't think you can do that, you're probably in the wrong field.
Thank you, sir.
You're welcome. Good. It was fun.
It's wonderful to speak with you.
Enjoyable afternoon.
I appreciate that.
Okay.
Take care.
Bye-bye.
Bye-bye. New update. Started a Substack. Writings on there are currently about language and ill-defined concepts, as well as some other mathematical details. Much more being written there. This is content that isn't anywhere else. It's not on Theories of Everything. It's not on Patreon. Also, full transcripts will be placed there at some point in the future. Several people ask me, hey Curt, you've spoken to so many people in the fields of theoretical physics, philosophy, and consciousness. What are your thoughts? While I remain impartial in interviews, this Substack is a way to peer into my present deliberations on these topics. Also, thank you to our partner, The Economist. Firstly, thank you for watching. Thank you for listening. If you haven't subscribed or clicked that like button, now is the time to do so. Why? Because each subscribe, each like helps YouTube push this content to more people like yourself. Plus, it helps out Curt directly, aka me. I also found out last year that external links count plenty toward the algorithm, which means that whenever you share on Twitter, say on Facebook, or even on Reddit, etc., it shows YouTube, hey, people are talking about this content outside of YouTube, which in turn greatly aids the distribution on YouTube. Thirdly, there's a remarkably active Discord and subreddit for theories of everything where people explicate TOEs, they disagree respectfully about theories, and build as a community our own TOE. Links to both are in the description. Fourthly, you should know this podcast is on iTunes, it's on Spotify, it's on all of the audio platforms. All you have to do is type in theories of everything and you'll find it. Personally, I gained from rewatching lectures and podcasts. I also read in the comments that, hey, TOE listeners also gain from replaying. So how about instead you re-listen on those platforms like iTunes, Spotify, Google Podcasts, whichever podcast catcher you use. And finally, if you'd like to support more conversations like this, more content like this, then do consider visiting patreon.com/Curt Jaimungal and donating with whatever you like. There's also PayPal, there's also crypto, there's also just joining on YouTube. Again, keep in mind, it's support from the sponsors and you that allow me to work on TOE full time. You also get early access to ad-free episodes, whether it's audio or video. It's audio in the case of Patreon, video in the case of YouTube. For instance, this episode that you're listening to right now was released a few days earlier. Every dollar helps far more than you think. Either way, your viewership is generosity enough. Thank you so much.